Realize how much work I have to do marking nearly 400 papers every week or every Monday and scan them and email them to you. So I would really appreciate you could hand in your stuff in the morning of Monday, right? So that will give me plenty of time to mark everything and scan everything and email it to you on the same day, right? I hope you follow what I'm saying. Yes. Yeah.
There's supposed to be some on the right hand side somewhere. They are.
I don't know. I mean, every time I come here, it's not on, so I don't know what's happening. Hello, guys. Can you also increase the volume for this?
Hang on a minute. Testing.
Okay. Can you increase the volume for this? Good morning, good afternoon, guys. So last Thursday we talked about point estimation.
I don't have the controls for that room.
Okay. So you remember this is stuff we did on last Thursday, which you weren't here. These are the four elements of estimation: the population, the sample, the parameter, and the estimator. And I looked at an example where we were looking at the average height of men in Manchester. And suppose you select 3 people at random and measure their heights and call them x1, x2, x3, right? Then the possible estimators for theta could be any of these and more, right? And the question rises, how do you choose the best estimator? I mean, if you have all these different combinations, all these different possible estimators, how would you know which estimator is good and which is not good, right? So to determine that, I introduced 2 criteria. One is called the bias and is defined as the expectation of theta hat minus theta. 2 is known as the MSC, or the mean squared error. It's defined as the expectation of theta hat minus theta squared, right? Now, suppose you have 2 estimators, say theta 1 and theta 2, and you want to choose between the 2. With respect to bias, if the absolute value of bias of theta 1 is less than the absolute value of bias of theta 2, then you would choose theta 1 hat, or you would prefer theta 1 hat. And if the MSC of theta 1 hat is smaller than the MSC of theta 2 hat, you would choose, once again, theta 1 hat. Okay? So this is how you choose which one is better. Then I talked about more definitions. You say that the estimator is unbiased if the bias is equal to 0. Right? And you say that an estimator is asymptotically unbiased if the limit of the bias is 0 as n approaches infinity. And finally, you say an estimator is consistent if the limit of the MSE as n approaches infinity is 0. Right? And I listed 3 properties. The first property is a decomposition property. It says that the MSE of an estimator can be decomposed as the variance plus the square of the bias. The second property is that if the expectation of theta hat is k times theta, where k is a constant, then theta hat divided by k is an unbiased estimator for theta. And the third property is that theta hat is a consistent estimator if and only if the variance and the bias approach 0 as n approaches infinity. Right? So these are, can you listen guys please? These are 3 properties I talked about on Thursday last week, and I also proved them. So you should know the proof of each of these, right? I'm not going to go through the proof. So this is the proof of the first property I listed. And this is the proof of the second property. And this is the proof of the third property. Okay? Now, what I'm going to do today, well, I mean, last week I did not have any time to do any examples, right? So today I'm going to start doing some examples on point estimations. So starting with example 1, right? Can you listen, please, guys? Stop talking, guys. All right, so you have a random sample from a normal distribution, and let's suppose that the sample mean x bar is an estimator for mu, the population mean, right? Now we want to derive the bias and the MSE. All right, first let's consider the bias. Remember, the bias is the expectation minus the parameter, right, which is okay. Now, what's the expected value of xi if xi is normal? Yes? Talk to me, guys. What's the expected value of xi? It's mu, right? All right, so this is 1 over n times mu minus mu, which is 0. So what this implies is that x bar it implies that the sample mean is an unbiased estimator for the population mean. Remember, unbiased means that the bias is equal to 0, right? Okay, now the next thing I want to work out is the MSC. The MSC of x bar, because of a property I proved last week, can be written as the variance of x bar right? This is the property number 1, right? I just mentioned. Right, the bias is 0. So this guy here is simply the variance of x bar plus 0, right? So this is variance of okay. You with me, guys? Now, if you take the variance inside, it becomes 1 over n squared times the sum of the variance of xi. Yes? Now, what's the variance for a normal variable? Sigma squared, yes. So this guy here becomes 1 over n squared times the sum of sigma squared. Yes? So this is 1 over n squared times n sigma squared, which is sigma squared divided by n, right? So the MSC, the mean squared error of x bar, is sigma squared by n, right? Now, the next thing I want to see is if the limit of the MSC is 0. So remember, if the limit of the MSC is 0, then we can say that the estimator is consistent. Right? The limit is indeed equal to 0. Right? So therefore, x bar is consistent. Right? All right. So what we have shown in this example is that the sample mean x bar is an unbiased estimator and also a consistent estimator of mu. Okay? You guys okay? Yeah. All right, the next example is I'm going to do, I'll take this away so you don't need to copy it down, so you know. Example 2. I mean, you learn mathematics by doing a lots of examples. So I hope the examples I am doing today will help you to learn better, right? Okay? All right, consider x bar as an estimator of theta. So here we have a random sample from a uniform distribution on the interval theta to theta plus 1. So the first thing we want to do, as in example 1, is to find the bias. is to find the bias of x bar, which is the expectation of x bar minus the parameter, right? You with me? Shout at me if you don't follow. All right. Now, for a uniform distribution, what's the expectation? You know, I'm sure you know from probability 1, which you did in the first semester. Do you guys remember? The expectation of xi, half of a plus b, right, which is what here? Is theta right, is for a uniform variable from a to b, the expectation is a plus b divided by 2. Okay, so if you apply this, this is what you get, right? So this is so is theta plus half minus theta, which is equal to half, which is not equal to 0, right? So hence, all right, hence x bar is a biased estimate of theta because the bias is not equal to 0. If the bias is equal to 0, then the estimator would be an unbiased estimator, right? Okay. All right. The next thing I want to show you is, all right. Well, I wouldn't go to the next thing now. Well, can I take this away, guys? You don't need to copy this down, guys. There's no need to copy it down. Example 3. Sorry? MSC? Well, because the bias is equal to half, right? The MSC, you can calculate the MSC, but it will not be consistent. The limit will not be the limit will not be 0. So that's why I decided not to continue in this case, because the limit. I mean, this lady here has a good question, because the reason I stopped here is because even if you calculate the MSC, the limit of the MSC is not going to be 0, because as you can see, the bias is half, and the limit of bias cannot be 0 because it's a fixed number, right? Okay. Okay. Anyway, next one. Suppose all right, this example is related to question number 5, which is due next Monday, right? So hopefully you will learn from this Now here, because you have a max, right, you can't just take, finding the, all right, let me show you why. To find the bias, of max, right, you need to take the expectation and then subtract theta, right? This is by definition, right? Now, you can't take the expectation inside the max, which is not allowed. It's not a valid operation. You can't, to take the expectation of this, the first thing you need to do is to figure out the distribution of the maximum, right? So I'm gonna put a box. I'm gonna start a box here. You see a lot of boxes coming. Right, you will see in a minute why I'm doing this, because I need to know the distribution of the max before I can work out the expectation. You cannot take the expectation without knowing what the density of the CDF is, right? So that's what I'm trying to do now. So let Z equal to this. Then the right is equal to this, right? Now, if the maximum is less than or equal to Z, what can you say about x1 and x2? If the max is less than or equal to Z, then x1 has to be less than or equal to Z, and x2 has to be less than or equal to Z. Right? You follow? Yes. Now, because x1 and x2 are independent variables, we can say that this is right. That's because of by independence, right? Now, what you have here, guys, x1, remember, x1 is a uniform variable, so is x2, right? What you have here is the CDF of x1 and the CDF of x2. Do you see how I got these two terms? Because for a uniform variable on the interval, this is of the following fact. If you have x, right, a uniform variable from A to B, then the CDF of x is x minus A divided by B minus A. I'm sure you know this. It's in the list of distributions I gave you at the beginning of this course, the first day of classes, right? So this is equal to Z minus theta squared, right? Yeah, are you guys with me? Oh, you lost? No? Yeah, okay. All right, so this is the CDF of Z. So the PDF of Z all right, I'm going to complete the box here. All right. So you see what I've done. I have computed the CDF of z, which turns out to be z minus theta squared. Now the PDF is just the derivative of the CDF. So if you differentiate this with respect to z, you will get 2 times z minus theta. Right? Okay. Now why do we need the PDF? Why do we need the PDF? In order to do the integration, right? Okay. So that guy here, all right, becomes the expectation of z minus theta, which is now for a continuous variable. Yeah. This is what you get, right? Are you guys with me? So this is the integral from theta to theta plus 1 of z times the PDF dz, right? So this becomes, we can pull the 2 outside. Right, this is what you get, right? Correct me if I'm wrong. So this becomes 2 minus theta. Yes? Now, am I right, guys? This is what you get, right? And this, by the look of it, is clearly cannot be 0. So the estimator z all right. So z is a biased estimator of theta. Is that clear? Or yes, sir.
The last fraction between the other denominator of 2.
Oh, you mean this one?
Yes.
Oh yeah. So it should be 2. Yeah. Thank you. Thank you, James. Yeah. All right. Any other corrections? Let me know. Do you guys follow this or no? No. You don't follow this, sir? Are you okay? Yeah. Come on, guys. So what I have done? Listen. What I have done is to find the distribution of the max, which is in the box, right? So I first found the CDF of z, right? And then the PDF, which is this one, right? And then I take the expectation of the maximum of x1, x2, which turns out to be this integral here, theta to theta plus 1 of z times the PDF, right? And if you do the integration, I know it looks messy. If you do the integration, this is what you get, right? And it's looking at this, it's clear that this expression here cannot be 0, right? Right? And therefore the max of x1, x2 must be a biased estimator, right? Okay. All right, guys. So that's example 3. Now, example 4. Maybe a little easier one. All right, consider x bar the sample mean. Right, the first thing we want to find is the bias. Right, which is this. So this will be now. Let me ask you, check your memory. What's the expectation of xi for a Poisson variable? Is lambda, okay? Right. So this get 1 over n times n lambda minus lambda, and this is 0. So what you have here is a an unbiased estimator for theta, for lambda, sorry. X bar is an unbiased estimator for lambda. All right, the next thing I want to do is to find the MSC. Right, because the bias is 0, we can say that the MSC is equal to the variance. It's equal to the variance of x bar, right? You know why? Why is this equal to variance? Yeah, bias. That's what I just said. Sorry. Okay. Yeah. All right, guys. So taking the variance inside, you get 1 over n squared variance of xi. Now, variance of xi for a Poisson variable, I'm sure all of you know. I don't need to ask you what it is. So this would be lambda, right? And if you simplify this, guys, it becomes lambda by n, which approaches 0 as n approaches infinity. All right? So the conclusion here is that x bar is a consistent estimator. All right, is this clear, guys, or no? I mean, this is relatively easy compared to example 3, which is, example 3 is a little tricky. That's why I gave it to you as a quiz number 5. I mean, you have more than a week to work on it. Yeah? I mean, the difference between, your right, sir. Yeah. The difference between example 3 and the quiz 5 is that in example 3 we just have two data points, x1, x2. In quiz 5 you have n, x1, x2 up to xn. So that's the only difference between example 3 and quiz 5. All right, next one. No need to copy this down. Example 5. So we're going to do like 10 examples today. No, just kidding. Shh. All right, so this here you have a binomial distribution. X has a binomial distribution with parameters n and p, and we consider x divided by n, x divided by n as an estimator for p, right? So the first thing we want to work out is the bias of x over n, which is the expectation which is 1 over n times the expectation of x minus p. Do I need to ask you what's the expectation of x for a binomial? You remember? Come on, guys. What's the expectation of x for a binomial is n times p, right? So did you follow me or what? Yeah. So x over n is an unbiased estimator of p, right? I'm disappointed with the number of people turning up for lectures. Why is that? Do they have an exam or what? Huh? Now, to find the MSC, because the bias is 0, we can say that this is the same as the variance of x by n. And this is 1 over n squared times the variance of x. So it's 1 over n squared. The variance for a binomial, I'm sure all of you know, is np times 1 minus p. So this is p times 1 minus p divided by n, which approaches 0 as n approaches infinity. So hence, right? You guys with me or not? Yes, any questions so far? Yeah? You're right. Okay. So this is example 5. Example 6. I mean, sometimes I will do only examples. So, I mean, the more examples I do, the better for you, because you learn the material, right? But you also have to do some examples by yourself. That's why I give you the quizzes, right? All right, here we have a random sample from a normal distribution with parameters mu and sigma squared. And we are considering this. You've seen this before, right? What is this known as? What's sample variance? We are considering sample variance as an estimator for sigma squared. All right, the first thing we want to find is the bias. Right? Now I'm gonna apply a trick here now. Guys, you see what I've done? I have divided by sigma squared and multiplied by sigma squared, so I haven't changed anything. The reason I'm doing this is because you must know, if you've been revising my notes, you will. What do you know about this? What is something special about this? I talked about in the lectures a couple of weeks ago, or maybe even last week. What do you know about this? It has the chi-square distribution with n-1 degree of freedom. Do you remember this or no? It's in the scan notes I talked about this. Come on, guys. I thought you have better memory than I do. Now, another property I proved in the class is that if you take the expectation of a chi-square variable is equal to the degree of freedom. So this is equal to n-1, which is 0. Hence, right? Hence, do you follow what I've done? I talked about the chi-square distribution in the last 2 weeks. If you look back in the notes, you will see it, right? One of the properties of a chi-square variable is that the expected value is equal to the degree of freedom. So the expectation of this is equal to n-1. So these two cancel out. So the bias becomes 0, right? Right. We got. Okay. Let me also find the MSC. Let me also find the MSC of S squared. The MSC of S squared is going to be the variance of S squared. Yeah, it's going to be the variance of. Why are you guys in a hurry to go? Are you not enjoying this or no? All right, it's equal to this, yeah? And All right? Okay, guys, you see what I've done? Because I introduced sigma squared inside, I need to multiply by sigma power 4. Right? That's because when you pull a constant outside, you need to power that to 2. And the same reasoning for the n minus 1 squared, because when you take the n minus 1 outside, it becomes the square of it, which is n minus 1 squared. Right? So this is sigma power 4 divided by n minus 1 squared times the variance of a chi-squared variable with n minus 1 degree of freedom. Now, once again, a couple of weeks ago, I proved in the class that the variance of a chi-squared variable with a degree of freedom is equal to 2 times a, right? You remember that or not? This is 2 times n minus 1, right? That's because of the property I proved, right? So this becomes 2, which clearly approaches 0 as n goes to infinity. All right? Hence, s squared is a consistent estimator of sigma squared. All right, so this is example number 6. The next one, can I take this away? Sorry? You just give, you have 1 minute, guys. Just, why are you guys in a hurry to go home? Example 7. Right? Okay. Can you finish this before Thursday? I will see you guys on Thursday. But before that, you try to find the bias. Try to find the bias and MSC for this estimator. Right? Hello. Come on, you're late all the time. Oh, sorry. So it's okay.
I did it last time and it took them half an hour to turn up. So I think you just
Yeah.
I got a question.
Yeah.
You know it's called sample variance. I don't know how to pronounce it. Sample variance is n1 over n minus 1. Whatever, yeah. And if the like x1, x2, and xn is given in a very concrete form, like maybe x1 is